Okay, so I think we'll go ahead and start. Today we have Cody Martin, who's a student of Azer. He's going to be telling us a little bit about knock-group presentations and bi-orderability. I think today I moved out a little early, so if there are like questions.
Teach right up all straightforward. So
yeah, so there are like questions probably.
We'll make them quick.
Yeah, exactly. Okay.
All right, thank you. So
just talk really fast, and then we'll have plenty of time for questions.
That's okay.
It goes by seniority.
So today I'll be talking about coming up with a particular group presentation for knot groups, and basically asking the question of, can we put a bi-order on it? So basically what left order is it preserves the order if you multiply by elements on the left, given group G, and maybe this isn't like super formally written down here, but we'll call it a bi-order if it also preserves multiplication on the right. So maybe some examples. First, let's start with the boring ones. So your standard groups, as in maybe the real line with addition, integers with addition, with the usual order. So these are actually bi-orders, right? Since probably not too hard to convince yourself if you're abelian, your left order implies bi-order. Okay? So let's look at z squared here. So an example of your standard Lex ordering, right? So let's see here. Right, compare your first thoughts. If there's a tie, then move on to the seconds. So I'll be comparing this to the Klein-Bottom group in a sec. So a way to think about this is, you know, if you lattice this guy out, you get bigger as you go to the right. First look at what column you're in, and if you tie, you get bigger as you go up along each column. Okay. So something else you can do with z squared, and I think I want to call this our first order with z squared. So here's 2. Okay. So if you take your favorite vector with irrational slope, this will define also a left order on z squared. So it's probably not too hard to convince yourself that if you tie here, well, you can't tie here since v has irrational slope. Comparing it with this, what we're really doing here is first dotting with 1, 0, and if they tie, dot with 0, 1. So anytime you have pick up a rational vector, you kind of need 2 statements, such as this. Okay. So now for a fun fact without proof. Basically, as long as you don't have torsion, if you're abelian, you're bi-orderable. So not too interesting. So now for something that is left orderable but not bi-orderable. So let's consider the Klein model group. So there's a couple of different presentations, common presentation for this. I'm going to use this specific one. Yes?
For that fact, the statement is that every torsion free abelian group admits a bi-order, or
Yeah.
that every left order is actually a bi-order?
I think both those are true.
Both. Okay.
Yeah. Since, well, if you're abelian and left orderable.
Oh, I see.
Yeah.
Yeah, okay, okay, sorry. Why do we need torsion free?
Torsion free. So I'm going to make a little side note here. Since it's a total order, well, you either have this or the other inequality, right? If g to the n is 1. Yeah.
Okay.
Right, like you're gonna run into issues basically. I guess this would be assuming that g is less than 1, but opposite. Yeah. Okay, so this presentation comes from identifying sides of squares like so. Which one do I want? This. So you can apply SVK, right? And you'll get this group to pop up by doing so. So let's attempt to put a bi-order on this. Okay, so a couple of observations is rewriting this relation. We like, maybe I'll go here. So right, we can right multiply by y and then right multiply by x inverse. We can rewrite the relation like this. Also, left multiplying by a couple of things, we can get this as well. So a way to think about this relation is every time you want to slide x past a y, you flip the sign. So it's not too hard to argue from here that given an arbitrary word in the group, so some word with x's and y's in it, arbitrary powers, they exist unique, mn and z, so that I can write my group element like this. So basically just keep sliding all the x's past the y's until they're all from. I guess that's only existence, but you can argue to assume that G has another representation like this, and you'll get a contradiction. So, okay. So since we're looking at putting a left order on this, it might be a good idea to see how the multiplication behaves. So we know that we can write any group element like this, and another one maybe like this. So using this relation right here, we want to slide the x to the m2 power to the left past the y to the n1. So that -1 to the n1 is from moving this past all the y's, and then we get. Okay, so if this group was, well, a little more well-behaved, maybe if this wasn't a negative sign here, we would have just a direct product. Think of these as ordered pairs, right? So being off by a sign here is kind of telling us we have a semi-direct product. So for a little review, maybe I'll just do it through this example. So here's another way to write our group. Y. So all this is here is we either send M2 to itself or negative M2, right, depending on the power of that. So this is another way to express the group. Okay. Make sure I have the right stuff here. All right, so here's a left order that'll work for this guy. You have to account for the sign change. So let's define so this is going to look awfully similar to Lex. First, note that the Y's are kind of more stable, right? Like, so maybe it'd be a good idea to compare them first. However, if there's a tie, here's where we want to be a little more careful. So the reason why you want to kind of define something like this is maybe I'll do a quick example with specific group elements. Okay. So if we have an even power on y, basically anything bigger than squared here this will be a bigger group element. So maybe 10. So to kind of see how this will preserve the order, I think the interesting case is if we multiply by an odd power of y. Let's multiply both sides by y cubed, for example. So when you do this, and take account to the fact that, well, 3 is odd, we're going to get x to the negative 2 divided 7 is less than x to the negative 10 divided 7. And yeah, note that our order is preserved here because now we're odd. So we look at which one of these guys is smaller, according to the rule over there. So maybe not super formal in writing all the cases, but this is basically the only bad case you have to worry about is when you multiply by like an odd power of y. Okay, and if you want a picture of this, kind of comparing this, here's like a pictorial way to kind of picture the order. So I guess I'm going to use my x's and y's are flipped from what they normally are, I guess, but no big deal. These should be powers. So like before, since you're comparing the y values first, first look to see if they're on different columns, and the further right or column you're on is going to be the bigger thing. However, on even columns, you get bigger as you go up. And on odd columns, from that rule over there, you're going to get bigger as you go down. So a kind of neat thing about this is you can kind of see the Klein-Bottle relation going on there, like in the order. Finally, I should probably show that this is not a bi-order. And for that, I'm going to need a quick statement here. I forgot my heading. So given a left order on G, it turns out that being bi-orderable is equivalent to the order being preserved under conjugation. I think I need a little definition here. So I'm going to let P stand for the positive cone. Basically, it's everything in the group that's bigger than 1. So being bi-orderable is the same thing as HN element of the positive cone implies that GH, G inverse is in the cone for everything in the group. Okay? So I guess I should argue that any arbitrary left order on the Klein-Bottom group can't be a bi-order. So suppose we have an arbitrary order. Yeah, for the sake of contradiction. All right, so since we're a total order, either x is bigger than 1 or x is less than 1. So the argument basically works the same for both. I'm just going to say, without loss of generality, x is bigger. So if we're assuming we have a bi-order, conjugation should preserve this. So let's conjugate that by y. However, if you apply the relation in the Klein bottle, yx, sorry, flip this side there. Conjugating x by y gives us x inverse. So this will imply this is equal to x inverse, that x inverse is equal. And this is a contradiction. So basically the argument boils down to either both x and x inverse are bigger than 1 or they both have to be smaller than 1. And that's not possible. I guess a way to see that is, since we're left orderable, right, multiply both sides by x inverse. So yeah, if one's bigger than 1, the other one has to be smaller. Let me see. This being my first talk, I kind of had issues on maybe getting the timing down, so I think I'm going to skip other examples of left orderable groups that are non-abelian and get to session 2. All right, so basically we're going to work with the concept of Archimedean groups, meaning that, well, I'll get to the definition. So we're going to call a left order in G Archimedean if for any arbitrary elements in the positive cone, so they're both positive, basically we can multiply G times itself to get it bigger than A, or bigger than H, excuse me. Okay, and we need a few more things here. So I'm going to define the absolute value. Basically, will be what you think it should be. We're going to let this be G if G is positive, or G inverse if G is negative, if G is not positive. Okay? So I'm going to need this here. So if we can find, well, elements in G such that no power of G gets us above H, we will say that G is infinitesimal. with respect to each. Okay? And notation for this is a double lesson. So there's Archimedean. And
Sorry, on that infinitesimal, what's the condition of the n again? Every n? Or
yes, yes. Yeah, thank you. Forgot that. Okay. So maybe some examples. So I put 2 orders on z squared. So let's go back to the lexicographical one. Right, so this guy definitely has infinitesimals. A way to see that is, well, from the definition 0, 1 and 1, 0 both in the positive cone. And I can really replace this, I guess, with any integer. And no matter how many times you add 0b to itself, it's never going to be bigger than 1, 0. So this is like for fixed b. However, with the second order, if you're ordering with respect to dotting with a vector with a rational slope, I should say, not quite that. If all the entries are rationally independent, you won't have any infinitesimals. So the second order doesn't have it. Sorry. I guess I'm not going to show why, but you can sit down and, well, assume that you have an infinitesimal and kind of do a fraction argument with the irrational vector. Go on now. And now for something that kind of blew my mind the first time I saw it. Just because it seems like such a strong statement. Maybe I'll shorthand it a little. So, hand me any Archimedean left order. Not saying it's a bi or anything. So this implies that the group's abelian. Yeah, this is very like non-trivial to prove as well. Converse is false because, well, z squared is an abelian group that has this non-Archimedean order right here. And now a definition to actually get to the heading of this section. So here's our kind of work to build the subgroup of infinitesimals. So for g in the positive cone, we're going to let, well, g, subscript g, to be everything in the group that is infinitesimal with respect to that g. So in general, this won't be a subgroup. However, if we assume some suitably nice things, that'll be the case. So bi-orderable alone will make this a subgroup. However, if you assume you're finitely generated, we actually have a normal subgroup. So S and S prime are basically, they're finite symmetric generating sets. So no conclusion yet, I'm just kind of getting finally, let G and G prime be in their respective symmetric generating sets. Oh, this is atrocious. Okay, so basically the punchline is that the infinitesimal subgroups with any greatest element in a finite symmetric generating set will be normal. Well, excuse me, will be a normal subgroup. And the choice of the symmetric set doesn't matter. Yeah. So if I have a finitely generated group, this choice does not matter. So it doesn't matter which one we take, right? So I'm going to let IG be this subnormal subgroup. Okay, so let's see an example of this in action. So consider Zn with Lex.
Sorry, just to make sure, when you say S is symmetric, that means if G is an S, then G inverse is also an S?
Yes, yes.
Okay.
So if I'm doing Lex as in thinking from left to right, like first we compare the first slot, then second slot. So if you take any guys like this and add them to themselves however many times, this will always be a 0. So, and I guess here I'm taking my finite symmetric generating set to be this. Wait, I guess I should. So right, like a 1 in one of the slots, and then it's negative since we're symmetric.
Can I ask a stupid question, Cody?
Yeah.
So for like R, G sub G would be all of R with the standard order.
R with the standard order, so only 0.
Yeah, so every H will work, right? Like
What do you mean by every H?
for the identity, you can always find an element in R. It's like H is the thing that's not the identity, right? Oh, sorry, just 0. My bad. I got the thing switched around. My bad. I got the thing switched around.
Yeah, if you add 0.
Okay, yeah.
Can't ever get positive. So.
Is R finitely generated?
No. No, I just.
I don't think it would apply to you anyway.
Yeah.
No, I'm just looking at the definition. Yeah, but R is definitely not.
Yeah, since we're normal, we can look at the quotient. So in this case, we mod out by. We get Z. And the quotient must be Archimedean, because we're killing all the infinitesimals. All right. A little bit more before getting on to knots. I promise. So a few technical propositions, and then we'll be there. Oh, So safety remarks first. Since we're killing off all our infinitesimals, this quotient's always abelian. Two, since this is abelian, we have kind of for free that the commutator subgroup is a subgroup, or I shouldn't say subgroup, is contained in the infinitesimal subgroup. So I'm going to be using this in a second. So a couple of technical propositions. So if G is finitely generated and bi-orderable, and we have some automorphism from G to itself that preserves the bi-order. So at alpha, so then these following two groups are also bi-orderable. Okay, one more. So kind of piggybacking off this statement here, if my group, after, well, modding out this, if we get like z to the n, we have this statement about bi-orderability. So hand me any integral invertible matrix. So if this semi-direct product happens to be bi-orderable, then the matrix A has at least one positive eigenvalue. Okay. So section 3, talk a little bit about Seifert surfaces. So what is a Seifert surface? It's a surface with boundaries such that the knot is a boundary. Like for example, I brought these that I kind of made by hand. So if you trace the boundary of this guy, you get the knot 6,2, and here be 7,6. So I plan to fully go through the trefoil knot example and building a group presentation for it. So I guess I'll kind of state one for the on knot. So the on knot is just the circle. So examples of Seifert surfaces for this guy would be, well, you could do a disk. And they're totally not unique because you can always add handles. So we can take the torus, cut out a hole, and on that boundary of the hole we have our knot. So these would both be Seifert surfaces for K. So there's actually a fantastic algorithm giving you enough to count these. We'll kind of see it on the trefoil. So what is an HNN extension? This is something that was in my title. It's basically a generalization of a semi-direct product. So I'll write the definition up. Here's the motivation. So we have this space or group, I guess you could say, G. Suppose we have, lying inside of it, two subgroups. And these subgroups are isomorphic. Maybe I'll give that a name. We'll call it alpha. Okay? So from this, we can construct a new group that by gluing A and B together by this map. So here's the definition for the HNN extension given this map in subgroups A, B, and G. So suppose our original group G has generators S and relations R. So here's going to be the new group if we glue these together. Or it's a way to write out the presentation. It's our old generators plus a new one. And then we have our old relations. And then we're going to have a whole bunch of other ones. So basically take everything in A and add this relation. So where A, or I should say for all. What was that?
Not necessarily.
Not necessarily. All the examples are the example I do is. But. So if A and B are just the whole group, I'm kind of saying that we're going to just write this. This guy's the exact same thing as basically taking the semi-direct product. So you want to think of T as being the generator of the C here. So T acts on A by, well, sending it somewhere else, according to what the automorphism does. Okay. Another example that I don't think So using an HNN extension, I'm going to try to build a presentation for the fundamental group of the complement of the trefoil. So our trefoil looks like this. I want to make sure I have the right-handedness, and not the other one. All right? Well, first of all, I'm going to deform this a little to kind of make it a little more friendly for getting a cipher surface. Okay, so another way to kind of drop the same thing is, okay, I want to go over with this under, back. Basically, if you play it around with the string, you could show that these are the same number. So our trefoil is called 3-1. So suppose we have that orientation. Okay? So a way to build a ciphered surface is to follow the following algorithm. Start on any one of the arcs and follow the arrow. Whenever you come to a crossing, jump arcs. So for coming along here, let's jump to this one. And you want to go on the side that respects the orientation. So if we do the same thing in this one, we're going to jump down, and come back. And fill this guy. We basically have a disk. So if you do the same thing with the remainder, like maybe going down this and doing the same process, you kind of get a mirror on the other side. Now what you do is you connect, this will be our side here. You connect these two with a twist that is in the same direction as the crossing. So let's see here. And I think there's something important in the Seifert surface definition I forgot. It needs to be oriented. Yeah. Note in this case we do have oriented. So this algorithm will always work actually. Okay. So in the remaining time, I'll talk a little bit about using this HNN construction extension to get our presentation here. So here's the construction. Be a little fast here. Since this is orientable, it makes sense to, well, maybe thicken it and talk about top and bottom side. So we're going to consider this guy here. So basically take this guy and fatten him. And you want epsilon to be small enough so you don't get any like weird self-intersections or anything like that. Okay? Then, to recover the knot K, we can glue the back face to the front face. So maybe I'll drop our on-knot example. So we thicken it. If you glue the top to the bottom, what you're left with is a ribbon with a, well, think of it as a tube with a slit in it. Which is going to be homotopy equivalent to your original knot. Okay, so I'm going to go about, get a little rush now. So this is homotopy equivalent to the wedge of two circles. Basically, you can shrink to the middle along the bands and collapse each of these. And
you can probably do a second talk this week.
What was that?
You can probably do a second talk in 2 weeks, right?
Yeah.
Right? I was scheduling for the week after.
Yeah, Aaron is talking, but then there's some stuff going on in April, right? April is like that for us.
Because instead of hurrying this, it might be more reasonable to
Yeah.
do a second talk. It doesn't fit.
Yeah.
So you want to stop?
Sorry, my timing. Yeah, let's
Okay.
definitely. Sorry, my timing was a little off, but yeah.
Okay.
Good for practice.
Well,
So,
let's definitely okay.
continue next time. So I'll definitely maybe restate some stuff in a little more